If you subscribe to the channel, you'll get lots of interesting videos like this one. And if you like the video, it'll really help us out. Please comment down below for any other interesting things. That also really helps us out as well. Hi, welcome to another edition of Easy Theory. So one question that I'm asked quite frequently, is, because I do PDAs to CFGs on the street, obviously, is when we do this conversion, how big is the CFG going to be? Because if we looked instead at the CFG to PDA process, we had these 4 base states. If you remember, we had these 4 base states and a chain of states for every rule. And so we can actually infer the size of the PDA because we're going to always have these 4 states here, and whatever the total size of all the rules is, that's effectively, we can figure out what the number of states that we're going to add or the number of transitions that we want. So we can actually figure out what the PDA size is going to be. But if we do the same thing for the PDA to CFG process, what do we actually know? So let's just say that, for example, that the PDA has n states and s stack symbols, because remember that some of the rules that we use are entirely dependent on whether there's a pair of matching transitions. Okay, so let's actually think about this. So for type 1 rules, we're going to have a sub q, I'm going to just call it q here, going to epsilon for each state q. So that means because there are n states right here, this means that type 1 is going to have n rules that are generated. And also, one thing that we should note is because we can have any state in either coordinate here, this tells us that we're going to have n squared variables. Some of them may be totally useless, like if one state can't reach the other, but in general, it could theoretically be that one state can reach another. So I can't discount some of the variables here in general. But yeah, so we're always going to generate these n rules right here. All right, so then what about for type 2 rules? So type 2. So here we're going to have a sub, I'm going to call them P and Q. And the recipe says to have something like this, where the first state P here is the first one of the first variable on the right side. Q is the second one of the second variable, and the 2 in the middle have to match. For each triple of states P, Q, and R. Okay, and this is not dependent on the structure of the PDA. So in these P, Qs, and Rs could be the same. They don't have to be different. So in fact, what we can see kind of clearly is that this will generate n cubed rules. Okay, so if I have 10 states, this is going to have 1,000 rules. Okay, it's a lot, but we can determine how big it'll actually be. Some of the rules definitely could be totally useless, but we can't actually discount them without knowing something in advance of the PDA, which we don't have that luxury right here. All right, so then what about for type 3? So if we have a transition, oops, not Q first, it should be P first. So if we have something like this, where we have 2 transitions, where the first one is going to, let's say, it's not going to pop anything because every transition either pushes or pops, and this one pushes. Let's say it pushes X, and the other one will pop the X. Okay, so then the rule that we add, of course, is APQ goes to A, because that's what we read on the first one, ARS, because that takes us from this state to this one, and then B, which is what we read on the pop transition. So the question is, well, how many rules does this actually make? Well, let's see. So it seems like this tells us that it should be, well, we have any quadruple of states, and they all could be the same. They could be different. It could be any choice of 4 states. So this will, let's just say, have n to the 4, because that's the number of possibilities of states. And it could be any of the stat characters. So, and because they have to match on both sides, this will be times s, and then the number of input symbols. So let's say that the size of the input alphabet here is B. Actually, I shouldn't use B because I've already used it, B. Let's call it Z. So then we could have anything for what's being read here or not. It could be epsilon too. And then anything here or epsilon. So times, it could be any of the Z symbols for each one of them plus 1 for epsilon squared, because they could be independent. And you may declare victory and say that that's the number of rules that we'll actually make here. But it actually is not necessarily that. Okay, so this is a red herring right here. Why? Because this is dependent on what transitions there are. It may not be that every transition is present, right? In fact, the example that we did before doesn't have every transition out there. In fact, what if we had a PDA with 0 transitions? Or actually in our construction, we have to have 2 because we push on the special symbol at the beginning and pop it off at the end. So those 2 have to be there. But other than that, there might not be any transitions whatsoever. So in fact, the lowest this could be, I guess, from our construction would be 2 transitions, which means 1 pair of matching transitions, which means we'll add 1 rule. But it could be that every possible transition is present, and therefore we would have this many. So the answer is we don't know in advance. So the true answer is, so let's say that the true answer for a given PDA is, let's call it chi. So that's just a Greek letter, or yeah, I think Greek letter that is often used to denote something in math. So it's always going to be at least n cubed plus n plus 1, where the n cubed comes from type 2, the n comes from type 1, and the 1 here is the minimum for type 3. Oops, I don't want those. So this is going to be the lowest that chi can be, but it could be at most this number right here. So the highest it could be is n cubed for type 2 plus n to the 4th times s times z plus 1 squared. So this is the lower bound, and the, actually I should say here, so this one is the maximum for type 3. That's the maximum possible, because we can't have any, we can't have 2 transitions that are literally the same between the same 2 pairs of states. There can only be at most 1. And if we put them all in, you can actually make this number a little bit smaller, because you can actually notice that in the construction, I guess I don't have it, there's nothing exiting the single final state, and there's nothing coming into the new start state. So you can actually make this a little bit smaller, but it's effectively the right answer. It's asymptotically the right number here. So hopefully that was interesting. Leave your comments down below about the PDA to CFG process. As always, please like and subscribe to the channel. It really helps us out. There are a lot of other links in the video description if you want to help us further. And as always, I'll see you next time.